Have you ever wondered why certain materials attract other substances while others repel them? This fascinating dance of attraction and repulsion revolves around the concept of surface charge, an invisible force field that governs these interactions. From the static cling of your clothes to the way oil and water refuse to mix, surface charge plays a major role in our everyday lives. Today, we'll unravel the mysteries of surface charge, the point of zero charge, and their intriguing effects on adsorption. Let's dive deeper into these fascinating concepts. Surface charge, an intriguing concept, plays a role in a wide range of contexts, from chemical reactions to biological processes. But what exactly is surface charge? It's a fascinating phenomenon that arises when there are excess protons or electrons on the surface of a material. Imagine a party where there are more people in one corner than the rest of the room. That corner, my friends, is analogous to the surface with an excess of protons or electrons. This party imbalance impacts how the material interacts with its environment. For instance, it influences the attraction or repulsion between the material and other substances in its vicinity. It's like the popular corner attracting or repelling more partygoers. In the same way, surface charge can attract or repel ions, molecules, and even biological entities, forming the basis for many chemical interactions and biological processes. So, now that we understand surface charge, what about the point of zero charge? The point of zero charge, another fascinating concept, is the pH at which a material's surface charge is neutral. Now let's dive a little deeper into this idea. The point of zero charge is a critical factor often determined by the balance of acidic and basic functional groups existing on the material's surface. Picture a seesaw with acidic groups on one side and basic groups on the other. The point of zero charge is that perfect balance point where the seesaw sits perfectly level, neither side being heavier. This balance point is not just a theoretical construct, but plays a significant role in real-world scenarios. It determines how a material behaves in different pH environments. For instance, if the pH is below the point of zero charge, the surface becomes positively charged. Conversely, if the pH is above this point, the surface becomes negatively charged. So how do these concepts affect adsorption, you ask? Well, let's find out. Adsorption, a critical process in many areas, is greatly influenced by surface charge and the point of zero charge. Now let's delve into how these two factors come into play. Imagine a surface charge as a magnetic force field around a material. Depending on its nature, it can either attract or repel other substances. When the surface charge is positive, it will attract negatively charged substances, and when it's negative, it will attract positively charged substances. Now, the point of zero charge is a bit like a balancing act. It's the pH at which the surface charge of a material becomes neutral. At this point, the material doesn't preferentially attract positive or negative substances. It's a bit like a party where everyone's invited, regardless of their charge. These two factors, surface charge and point of zero charge, are key players in the game of adsorption. They determine the ability of a material to attract or repel other substances. And this has some pretty practical implications. Take water treatment, for instance. By manipulating the surface charge and point of zero charge, we can enhance the adsorption of contaminants and make our water safer. In catalysis, these factors help us control the reaction rates, and in drug delivery, they can help us design more effective drug carriers. So, next time you see a substance sticking to another, remember the invisible forces of surface charge and point of zero charge at work.